In this paper, we presented an explicit finite element method for solving Navier-Stokes-Brinkman equations. With the development of micro-CT imaging techniques, we can now have access to the pore space with an increasingly fine resolution. It is possible to perform numerical simulations directly on the images. This new approach, named digital rock physics, is recognized as a replacement to conventional laboratory approaches and provides a better understanding of the rock properties. Popular CFD approaches includes the lattice-Boltzmann method and finite volume method. Yang et al. 2019 first used the stabilised finite element method for solving the Navier-Stokes equations on 3D micro-CT images. In this work, we further extend the method to solve Navier-Stokes-Brinkman equations on grayscale. Why we are interested in Navier-Stokes-Brinkman equations? The presence of different length scales and large contrasts in permeability leads to highly ill-conditioned equations, which are difficult to solve. These equations are typically used for model the fluid flow in porous media featuring open channels or fractures. Similar problem happens on digital rock physics. If we approximate the flow by a Darcy's law, we can have the so-called Navier-Stokes-Brinkman equations. In general, there are two approaches to solve it: two-domain approach and unified formulation. In the two-domain approaches, two different sets of governing equations are used to describe the flows in the fluid and the porous domains. Classically, Navier-Stokes equations are solved in the free regions, whereas Darcy equations are solved in the porous regions. The set of equations are completed by interface condition to enforce the continuity. Many researchers also worked on unified formulation of Stokes-Darcy equations. In this work, we propose to implement a stabilized FEM by using the variational multiscale approach, which consists in splitting the unknowns in large-scale and subgrid scale components. It allows the use of linear equal order velocity and pressure interpolation, the same nodes, which is ideal for describing the boundary condition. The stabilization parameter, that may affect the velocity field, has been discussed and an optimal parameter was chosen. The fully explicit matrix-free finite element implementation is ideal for parallelism on high-performance computers. The implicit Darcy term allows the use of larger time stepping. We analyzed the influence of the micropermeability field on the regime of the flow. These benchmark tests provide guidelines for choosing the resolution of the grayscale image and its segmentation. With the filtered grayscale image, we perform a three-phase segmentation to identify the microporous phase by using two thresholds. The threshold values have to be chosen carefully, since better spatial resolution and variations in the threshold value for binarization have been reported to change the estimated permeability significantly. Once the three phases segmentation is completed, the solid structure is mapped by the microporosity. The micropermeability field can be calculated by Cosen-Ackermann relation. We solved the three-dimensional grayscale micro-CT images up to 800 cubic voxel using hybrid OpenMP/MPI implementation. The memory cost of this algorithm is low due to the trilinear continuous velocity space and matrix-free implementation. These simulations show that although this Berea sandstone contains only 2% of microporosity, its influence on computed permeability is already significant. A higher impact is expected for complex multiscale rocks such as carbonates that are likely to present a high ratio of microporosity.